Hi, I'm Shale, and I'm here with Gerardo and Tristan to show you our Extravaganza project on a fulcrum-based scale. For our Extravaganza project, we looked to measure the torque force on a rigid body. This was done to find the equilibrium of this seesaw mechanism. By slightly changing the masses and the distance from the fulcrum point, we were able to determine the required distance for equilibrium to occur. By comparing these masses and distances, we will be able to compare the overall torques and rotational motions of the seesaw. This was ultimately used to make a fulcrum-based scale. Torque is generated whenever a given force is applied to a rigid body away from its axis of mass. Torque can be defined as a force of an object that causes rotation. The magnitude of torque can be given by the following equation. F sine is the force in the perpendicular to r, and r is the distance from the center of rotation where the linear force is being applied. The torques of a system are in equilibrium when both the net torque and the net force are equal to zero. We hypothesized that to reach equilibrium, heavier objects will need to be placed closer to the axis of rotation compared to objects with a lower mass. This means that the markings of a heavier mass would be closer to the fulcrum and vice versa.
Thank you, Shale. So I'm going to go ahead and get us into our experimental design for our project, starting off with the materials. So the specific materials that we used in this project were tape, a fulcrum scale, plastic weights, dice, nails, a precision scale, as well as a ruler. Now, the dice and nails aren't something that needs to be used specifically for this procedure, but they were something of light mass that we had on us at the time, and they can easily be replaced by something of similar mass. So now moving on to the procedure, we started off by obtaining the fulcrum scale and placing a known mass on the right side of the scale. And this known mass remained constant throughout the entire experimentation, and it acted as our control for the project itself. So once we had our known mass on the right side of the scale, we then proceeded to place different masses along the left side of the scale at different positions to determine what mass at what position was needed to perfectly balance the scale. And once we figured that out, we recorded the masses on the actual scale itself. And then we moved on to the second part of the experimentation, which was determining the mass of an unknown object by placing that object on the scales on the left side to see between what positions at what masses would it balance the scale that according to the weight that was on the right side. And I'm gonna go ahead and give you guys a little demonstration of what that looked like now. Hey guys, so today I'm gonna go ahead and do a demonstration for you guys on our physics extravaganza project, which we can see here is a fulcrum-based scale. The values here on the left side of the scale are the exact masses that we've determined that will perfectly balance the scale according to the control weight on the right side of the scale. So what I'm going ahead and been doing for you guys is trying to determine the weight of this dice right here. So I'm gonna go ahead and start at the leftmost side and work my way down. So here we go. Okay, from that I could determine that this dice weighs more than 2.21 grams. Gonna go ahead and skip one. Okay, we can see that this dice weighs more than 3.4 grams. Once again, our dice weighs more than 4.18 grams. Okay, we can see that our scale is leaning a little bit to the left, which indicates that our dice likely weighs slightly more than 5.46 grams. Okay, here at the 7.02 gram mark, we can see that the scale does not move and leans all the way to the right, which indicates that the mass of this dice is likely in between 5.46 grams and 7.02 grams. Now I'm gonna go ahead and weigh out this dice and see how accurate our scale really is.
Just as I expected.
5.63 grams, which lines up with our scale. So we can determine that our scale is pretty accurate as the scale was leaning a little bit to the left at the 5.46 mark and leans all the way to the right at the 7.02. So we were able to determine that the mass of our dice was in between 5.46 and 7.02 grams. Thank you. So I hope you guys enjoyed that little demonstration video that we put together for you guys. Now I'm going to go ahead and get into the specific data that we were able to collect from experimentation. Here we have the mass that was used to balance at each position on the scale. And we have the distance from the fulcrum that that specific mass was placed at throughout the scale. And we have the torque that we were able to calculate by multiplying the mass used to balance the scale times the distance that that mass was placed at from the fulcrum times the acceleration due to gravity. And we were able to get some pretty good numbers as we were able to keep our percent error pretty low throughout the entire graph and throughout the entire fulcrum scale. And here we have another graph that represents the distance from the fulcrum compared to the mass that was used to balance the scale. And we can see here that as the distance from the fulcrum decreases, the mass used to balance the scale actually increases. And I'm going to go ahead and let Tristan get into some of those more specific details in the discussion. Thank you.
Now, I will touch upon some key points from the data. But the data table showed us that the net torque on the system is 0 because the torque on each side of the scale was determined to be the same with just some minor error. The graph also aligned with the formula for torque, which showed that the mass and distance from the fulcrum are inversely proportional to each other, given a constant torque. And lastly, the percent errors in the experiment were likely caused by the scale not being perfectly balanced due to not having small enough mass units to balance the scale. And as a summary, the hypothesis that heavier objects will be placed closer to the fulcrum and vice versa was supported by the data and the graph. As a note to future experiments, objects with less mass could be used to calibrate the scale to allow for more precise balancing, and a longer scale could be used to allow it to measure a larger ranges of masses.
Thank you for listening.